Easier than usual. Yes, yeah. Okay, we're going to finish up 3.4. Okay, so remember the idea here was we could use a basis to represent a coordinate system. So we know our 1, 0 vector looks like this. And if we do a bunch of copies of that, that can make up an x-axis. Turn it around. And the 0, 1 vector looks like this. If we do a bunch of copies of that, we can make a y-axis. So that standard xy coordinate system can be described by this basis. And then we said if we have a different basis, there we go. We can do several copies of 1, 1. So here's what 1, 1 looks like. And we can go backwards. That can be a new x-axis for us. And negative 1, 1, several copies, and their mirror images can make a new y-axis. So we can have a different coordinate system based on a different basis. So then I could take my two different coordinate systems, here and one here. And I could take, say, a vector like this. If I draw that vector in this coordinate system, I could say it's 7 over and 11 up. And I can use a matrix to represent that vector. Or I could take exactly that same vector. And this one is just in blue, 9 units this way and 2 units that way. So in this coordinate system, I could represent that same vector as 9, 2. So our notation for that, remember this is all review, is I've got some vector. If I represent it relative to the standard basis, I would use the matrix 7, 11 to represent it. And I want to emphasize this is the same vector. The vector is just the arrow. If I want to describe it relative to that new basis, it is 9, 2. And then remember our two coordinate systems here. S is 1, 0, 0, 1. That's B. It's the x-axis and the y-axis. If I want a matrix that converts B coordinates to S coordinates, I just take the vectors in B and use those to form a matrix. And if I want to convert a vector from standard coordinates to B coordinates, that's just the inverse of this problem. Okay. All of this should be review. Okay. And then this is the type of problem we ended last lecture on. Let's see. Let's write it this way. So we talked about if we have a transformation, a function that takes vector inputs to vector outputs, we can represent it by a matrix. And this matrix converts S coordinate inputs to S coordinate outputs. It's that matrix representation is relative to the standard basis. So before last week, we didn't even know there were other coordinate systems. Okay, but now we're going to work with a second coordinate system. What I want you to do is find the matrix for transformation when input and output are described relative to the coordinates. And I think a picture will make this more clear. Let's move this down. So this is the picture that we had before. You now want to decorate this and point out the fact that the matrix is taking S inputs to S outputs. Okay, and then we've got this new coordinate system. So we're going from B inputs to B outputs. And there's a matrix that's going to represent that. And that's what we're trying to figure out. Let's draw this picture again. Let's do a specific example, I think I can. Do it that way. So there's the 2, 4 input. Let's see. 3, 1. And then when I apply this matrix, that is 6 and 4 is 10. Oh, that's interesting. Writing that back. Write a copy here. It's just easier for me to see. 6 and 4 is 10. 2 and 12 is 14. So the idea is this same vector we can write in the input space like this. And that's going to go to the same output vector, which is going to be here. Okay, so let's see, this is over 3 and up 1. So the coordinates of that vector relative to the new basis, the input is 3, 1. And actually, hold on. Yeah, the calculation went off a little bit here. 2, 4. Yeah, it should be. Oh, it's, yeah, close it. 2, 4 is, yeah. Oh, it's not 10, 14. So we're going to find this one is over 12 and back by 1. Okay, so again, notice the input vector is the same here, just we have a different coordinates to describe it. And then the input vector gets transformed to an output vector. Same input vector, same output vector, just described differently. As we want the matrix that in this particular instance converts 3, 1 into 12, -1. Okay, let's draw that picture again. Oops. So we know we want to start here and end here. And instead of going directly across, we're going to turn this into a 3-step process. So the 3-step process is, put it this way. Convert B input to S input. Step 2 is to convert S input to S output. And then step 3 is to convert S output to B output. And we talked about each step here. So B to S is just the, oh, remember, our B basis is this. Our S input to S output was given as the 3, 1, 1, 3 matrix. And then going the other way, S to B is the inverse, which is 1/2, -1/2, half, half. Then we talked about we can, if we have a multi-step process, we've got a way, we have a matrix that represents each step. We've got a way to combine those matrices to make it a one-step process. And that is the matrix we're looking for. Okay, I want to do 2 more examples. And there's going to be reason for both of these. And drop that. So same picture. When we're converting standard input to standard output, it's the matrix. We're given that matrix. Okay, and then what's interesting here is, I'm going to exaggerate a bit. Well, it's hard for me to draw. So that's the y-axis, and then the x is like this. So down here, we're converting B input to B output, and we want to know what the matrix is. So once again, start here, end there, make it a 1, 2, 3-step process. And step 1 is to convert our B input to S input. And that's easy. I can just use the basis vectors of B to build my matrix. Step 2, S input to S output. That was given to me as part of the problem. And then standard output to B output is the inverse of this matrix. Let's see, 1/3, is that right? 1 + 2, yeah, 1/3. Let's see, -2/3, 1/3, 1/3. Put the 3 together. Five, 0, 0, -1.
So for the first part, how do you know that the B input and then converting it into S output? How do you know it's the matrix that you put in the first step?
So let's talk about this. I'm going to work with our earlier example.
Because I'm assuming that it's not just directly given exactly like the second step.
Oh, it essentially is.
Oh.
I mean, you're given your B like this. So all you need to do is convert it to a matrix.
Oh, okay. I wasn't sure because I just saw the second step and I was just a little confused. Like, how do you have the first step?
Yeah, so it's just take the basis and build that matrix out of it. Okay, one more example, then I want to step back this time. I'll do this. So I want to draw the picture. So remember the 4 fundamental subspaces that we had. Oh, do you remember what the 4 are? One of them is the null space. Column space. So yeah, that's just a gentle reminder. The 4 fundamental subspaces, column space, what else? Null space. Do you remember the other 2? Exactly. So the orthogonal complement of the column space and the orthogonal complement of the null space. And do you remember the easy way to calculate these? The complement of the column space is the null space of A transpose. Is that ringing some bells? And what about the null space of A transpose? Or the null space, the complement of the null space is, yeah, column space of A transpose. Good. And then where do they live? Column space of A, input or output? Let's back up. Null space. Is that a subspace of the input space or a subspace of the output space? Input, yeah. Okay, I'm going to use this for my y-axis. Column space of A. That's input space, input side or output side? Nope, column is the output. right? So if I have, how is it? 1, 2, 3, 6. And if I use, say, 5, 10 as my input, well, the calculation is done this way: 25, 60, 75. So to calculate, to go from an input to an output, I do a combination of the columns. I use the columns to build the outputs. Do you see it? So I'm going to use that for the x-axis of the output space. And then the complements live in the same space. So remember, the null space, the complement of the null space is the column space of the transpose. So my x-axis is going to be the column space of A transpose. And my y-axis here is going to be the null space of A transpose. So let me draw those again. So this time, we're going to be using one basis for the input space, one basis for the output space, and each axis is going to be one of the 4 fundamental subspaces. So on the input side, my x-axis is the column space of A transpose, and my y-axis is the null space of A. And over here on the output side, I'm going to make my x-axis, it's a different x-axis, the column space of A. And my new y-axis is the null space of A transpose. Occasionally that's referred to as the left null space. Let me organize this a little bit nicer. Okay, and then we're going to want to find the matrix representation, the matrix representation of the transformation if we write inputs and outputs relative to these bases. Let's just put the pieces together. So we'll do it on the outside. So if I wanted to look at everything I could build out of the columns, you see that a basis is 1, 3. Okay. And this is interesting. We know that these two are going to be perpendicular. And in R2, that's easy to work out. Or I think you can see it. So if I have 1, 3, 2, 6, and multiply by -3, 1. Oh, wait a sec. Hello. Yeah, that's got to be right. Oh, hold on. Why isn't this working? Column space is 1, 3. Yep, that's there. So if I want something in the null space, oh, null space of A transpose. That's my bad. So A transpose is written this way. So -3, 1 is an input that produces 0. Okay. On this side, so there's A. Let's just keep A transpose over here. The column space of A transpose is described by 1, 2. And the null space of A looks like this. Call it B hat. The basis for the input space it's going to look like this. And I'll call it B double hat, the basis for the output space. We're going to combine these. Okay, so the picture is when we're going from standard input to standard output, we use the matrix 1, 2, 3, 6. And let's see, what was it? 1, 2. So it'd be more like this. And then it's steeper over here. I use double hats on this side. Okay, so once again, I'm going to start on the bottom left, end at the bottom right. We make that a 3-step process. Step 1 is B hat input to S input. Step 2 is S input to S output. Step 3 is S output to B double hat output. And you can see the pieces. So step 1, oops, no, that's step 3. No. So there's the output space. So we do the inverse. That takes us across. Oh no, my bad. Okay. And then when you put all this together, remember the right order. And I'll let you fill in the details. One thing I want you to notice is for the 3 different problems that we did, that was one of the matrices, diagonal. That was another matrix we got, diagonal. And this is a diagonal matrix as well. So remember the horses and human example? We converted to the hypercentaur and anticentaur. It's the fact that an anticentaur had 0 heads was the sort of the easy way to solve the problem. What that translates to is the more zeros we have in the transformation matrix, the easier it is to use. The most zeros we can reasonably expect to get is to have a diagonal matrix here. So what we're going to be doing at the end of the course is we're going to be given the matrix that represents a transformation, and we are going to come up with the basis so that the transformation matrix relative to that new basis is diagonal. So, yes?
I get the mechanics of what we did with that last one, but what was it that we did?
Oh, it's, we calculated this again.
Just in a different way?
Oh, so for all of these, it's, we're given the transformation relative to the standard coordinates. And what we want to do is find the transformation relative to a new coordinate system. For the first 2, I gave you the other coordinate system. I just said, use this, use that. This one, I decided to show you a little bit behind the scenes about how we could possibly pick a new coordinate system. So this coordinate system, I used the 4 fundamental subspaces. Okay, so given a matrix that represents a transformation from S inputs to S outputs. What we want to do is we want to find a new coordinate system so that the matrix relative to this new system is diagonal. Okay, and then there's kind of 2 things that we want to happen. So one, we want the same coordinate system for the input space and the output space. And 2, we want our axes to be perpendicular. Okay, so that first example we did, and D is the letter I'm going to use here. So Notice we use the same coordinate system for the input space and the output space. And these are perpendicular. So for this one, it's both of our wishes came true. For the second example, 1, 2, 4, 3. It was equals, so was it? This time, the input coordinate system was equal to the output coordinate system, but they're not perpendicular. And then finally, that third example that we did, 1, 2, 3, 6. Here, the input coordinate system is different than the output coordinate system, but both sets of axes are perpendicular. Okay, so this is what we're going to be doing for the last several lectures in the class. We're going to come back to this. Sometimes the matrix you get is going to be nice enough so that you get both of these at the same time. And just as a layout, those special matrices where that always works, we're going to be talking about in 8.1 in the textbook. If we want the input coordinate system to be the same as the output coordinate system, or we always want a diagonal matrix. If we want the input coordinate system to be the same as the output coordinate system, and we're willing to give up the axes being perpendicular to each other, we're going to talk about that more in chapters 7.1 to 7.3. And if you want both sets of axes to be perpendicular and you want that matrix to be diagonal, use the four fundamentals, use the four fundamental subspaces. And this we're going to cover in section 8.3. So it's overall, this is a big deal. It's you've got the transformation. You're going to design your coordinate system to make the matrix relative to your coordinate system as simple as possible. And there's usually conflicting things you want for your coordinate system. So you have to make a trade-off depending on the type of problem that you're doing. And these are the trade-offs. Okay, so that is going to conclude chapter 3. No, actually, let me motivate. So let's call it. How are we doing on time? So I want you to imagine we're working in three-dimensional space. And this is the coordinate system I'm going to give you. So think about a new x-axis, new y-axis, new z-axis. And then just so we have something to talk about, one interpretation of a matrix is it represents a list of vectors. So the matrix version of this basis is this. And then I've got a vector v, which is 1, 2, 3. Okay, I'm going to show you three problems that we've looked at earlier. And I want you to notice these are all instances of the same problem. So write v as a linear. What is that? Is that forklift? Okay. Vectors in B. Find the coordinates of V relative to B. And so hopefully you see this. Is if I want to write V as a linear combination of vectors in B, that's what I want to do. Mystery number times 148 plus mystery number times 4, 7, negative 4. And those mystery numbers are X, Y, and Z. So I want to find the coordinates of V relative to B. It's just going to be those three scalars that we used. And if I want to solve AX equals 1, 2, 3, so I need to find X, Y, and Z that satisfy this. And this is the same thing. It's finding the X, Y, Z there. So we've done this problem several times and just reworded in a slightly different way. Okay, and for all of these, we have to solve a system of equations. So put it this way. So in this section, so now if the basis is nice enough, then we will have a much easier way to solve these problems. So hopefully one thing you got out of the last section was picking the right basis made the problem easier to solve. With the horses versus human example, converting to the coordinate system of hypercentaurs and anti-centaurs made the problem easier to solve. If we have any transformation, I showed you special base, given a few transformations, I showed you bases for each of those. So the matrix for the transformation relative to those bases was diagonal. So it's a general idea is we can pick our own coordinate system. And since there's lots of coordinate systems that we can pick, we try to choose one that makes our calculations much easier. Common problem we've seen earlier this semester is we're going to come up with a new basis, a new coordinate system, so this type of problem is easier to solve. So as a warm-up, so remember chapter 1, there are three main topics: equations, vectors, and matrices. I want to remind you a couple things that came up with vectors and specifically dot products. Do you remember what a zero dot product told us about the two vectors? Very good. So the picture you should have is the two vectors meet at a right angle. They're perpendicular to each other. And then another interesting fact, hopefully you remember this, to calculate the magnitude of a vector, it's the square root of the dot product with the vector itself, right? Hopefully you can see that. So if I wanted to compute the magnitude of 1, 2, 3, okay, so, and then 3, the definition of unit vector is the length is 1. And then it's from fact number 2. We can calculate the magnitude with the square root of a dot product. And if the square root is 1, then the original, what we took the square root of, has to be 1. Okay, so There's two things we really like about the standard coordinate system. First is that the axes are perpendicular to each other. The x-axis and y-axis are perpendicular. And two is we also like it, just like the standard basis, when each axis is defined by a unit vector. So that means that one unit along the new axis direction is the same as one unit along the original. And it's one unit for each of the axes. They have the same scale. New word. If we have a basis that has these two properties, all the vectors in the basis are perpendicular to each other, and every vector is a unit vector, we say that that basis is orthonormal. Ortho for orthogonal, normal for everything having length 1. Okay, and so let's call this our general problem. So I want to talk about solving the general problem with orthonormal basis. So I'll do it with 3 vectors. So in other words, is we want to find some scalars. So we scale U1 by a certain amount, U2 by a certain amount, and U3 by a certain amount. The scaled vectors added together give us V. Okay, I'm going to call these C1, C2, and C3. So before we get started, I want you to tell me what all of these dot products are. What's U1 dotted with itself? So U1 is a unit vector. Or if it's orthonormal, that means that every vector in the list is a unit vector. And what do we know if we dot a unit vector with itself? It's 1. And in fact, that's going to be for each of those. What do we know about U1 and U2? They're perpendicular to each other. So what's their dot product? right? So all of these dot products are going to be 0. Okay. So what I'm going to do is I'm trying to find the C1, C2, and C3. So I'll take this. Okay, I'm going to dot both sides of this equation by U2. So if I do V dotted with U2, C1, I'm going to distribute this in. U1 dotted with U2, C2, U2 dotted with U2, C3. Exactly. So what's U1 dotted with U2? U2 dotted with U2. And this one. So turning it around, I've got an easy formula for C2. And I can do the same thing. I can get that C1 okay, so what that means is I've got my vector V. I'm trying to write it as a linear combination of U1, U2, and U3. Instead of having to solve that big system of equations, I can easily calculate these coefficients. Okay, so going back to that earlier example, it actually made your life a little bit easier. You didn't notice it at the time. Is these vectors are all perpendicular to each other. Uh, 16 and 16 is 32. Yeah, so all of these have a magnitude of 9. So if I changed this slightly, and made these unit vectors, U1, U2, and U3. And then if I wanted to write 1, 2, 3 as a linear combination of these vectors, so this is 1/9 plus 8/9 plus 24/9. Let's see, what's that, 25. And this number, instead of having to solve those equations, I just do this dot product. And I get the scalar there. And you can do a similar thing for the third one. Okay, so I didn't realize it, But because the basis I gave you had perpendicular vectors already, I could easily convert it to an orthonormal basis. And then if I have an orthonormal basis, solving that original problem, instead of having to solve the entire system of equations, we can compute each of these numbers with just a dot product. Okay, so that's interesting. One last thing I want to show you. Oh, for this, before we start getting into the, oh, I guess we're going to stop here. So I'm thinking I'm working in three-dimensional space. And if I just grab those first two vectors, I've got a coordinate system for a two-dimensional subspace, which is a plane. And then if I've got a vector v sticking out here, there's the u1 and the u2. And that u3 vector is out here perpendicular. So essentially what's happening is I've got the v. I use u1 and u2 to get the projection of v onto this plane. And then I move in a perpendicular direction to get to v. So if I have v is some linear combination of these u's, this part, oh, actually, let's say W is the subspace with the basis U1, U2. Is this part is the projection of V onto the subspace. So we did projections earlier. So this is another way to calculate a projection. If you have an orthonormal basis for the entire, actually, if you just have an orthonormal basis for the subspace you're trying to project onto, is you can just do the dot product calculations for the coefficients. Okay, so sadly, our time is at an end. So what we're going to do in Wednesday's lecture is I'll show you how to take a given basis and convert it to an orthonormal basis. So you've got a subspace with a vector description, you've got the basis for it, and we'll come up with a second basis for that same subspace, but it's an orthonormal basis, and the orthonormal basis is much easier to work with. Okay, so we're done. And I'll see you either in office hours or Monday. I'll talk to you after class. What's that? Yeah, I'm going to show you how to use Sage Math on Wednesday. Zoom. Take care.